everyone. My name is Chelsea Finn. I'm an assistant professor at Stanford University. I'm sorry that we couldn't be together in person today, but I hope that we'll have an opportunity to meet each other in person at some point. Today I'll be talking about meta-learning from few-shot adaptation to uncovering symmetries. The core motivation of what I'll be talking about today is a gap between our current paradigm and our current reality. At least in machine learning research, our current paradigm is to take a training data set, train a model on this data set, and then ultimately evaluate this model as is, as a static model. In contrast, our current reality is that the world is constantly changing, from stocks to changes in supply and demand over time to robots entering different parts of the world throughout the course of their lifetime. So what I'd like to talk about today is whether our algorithms can handle the changing world rather than just simply deploying a single static model. Now you might be wondering, how does industry cope with such a changing world when we develop our algorithms to produce static models? Well, if you ask Chip Huyen, who works on machine learning in production, she would say that machine learning systems degrade quickly because of concept drift. And for online machine learning systems, we want to update them as fast as humanly possible. So clearly, the way that our techniques are being used is not the way that we intend when we develop machine learning algorithms in research. And if we have a mechanism to bridge this gap, to actually prepare models for this constant change in the data distribution, perhaps we would be able to have a much broader impact. One approach to solving this problem is to use fine-tuning. And fine-tuning works very well. From computer vision to natural language processing, we've seen large gains in accuracy, for example, when you pre-train on ImageNet, and large improvements in error rate when you pre-train on language modeling and fine-tune on other downstream datasets. More recently in robotics, we've also found that the same trend holds. If we pre-train a robotic grasping system with reinforcement learning and then fine-tune it on drastically different situations, including harsh lighting, transparent bottles, a checkerboard background, and even a change in the robot's morphology, we see substantial gains when we use fine-tuning. The downside, though, is that fine-tuning also has its limits. It requires a non-trivial amount of labeled data in order to adapt to these new circumstances. So what I'd like to talk about today is how we can start to bridge this gap. Can we introduce assumptions that allow us to generalize further with less data? And can we make these assumptions as mild and broadly applicable as possible, yet also powerful in what they enable? A core aspect of what I'll talk about is meta-learning. So with this in mind, my talk will have three parts. First, I'll give a brief overview of meta-learning and what it's currently capable of. I'll also talk about whether we can use meta-learning to capture equivariances to allow us to generalize further. And finally, I'll talk about whether we can fine-tune to distribution shift without any labeled target data. But first, let's talk about what meta-learning actually is. And to do that, it's helpful to look at an example. In particular, let's look at a few-shot image classification example. The goal here is, given one example of 5 different classes, essentially a little tiny training data set, can we classify new examples as being among one of those 5 classes? Unfortunately, if you train from scratch, or even if you fine-tuned on this data set, your model would probably overfit heavily to such a small training data set. So what meta-learning algorithms aim to do is they aim to essentially learn how to learn other tasks in order to prepare the model to perform this few-shot classification task. So for example, what we can do is we can take image data from other image classes and structure it into mini training data sets and test sets. With this data, with these training classes, we can train a model how to learn from small amounts of data. And then after learning how to learn or meta-learning across these tasks, at meta test time, when given held out test classes, we give you a training data set from a held out test classes for this new task, it can effectively generalize to the new examples. Of course, this is an example specific to image classification, but you could also replace this example with problems like regression, language generation, skill learning, and really any machine learning problem. Now, this is how the problem setup looks like. How do meta learning algorithms actually solve this problem? One approach is to parameterize the inner learning process using a neural network itself. So you can take the training data set and pass that data into a neural network model and train the model to essentially learn from that data such that when it's given a new example, it can effectively predict the correct label and generalize to that test example. So this is one approach. Another approach to bring a bit more structure into this inner learning process is to embed an optimization inside the learning process. So instead of parameterizing the learning process as a neural network, we can parameterize it as an optimization process with some trainable parameters. So for example, we may have an initial neural network. We can run gradient descent on our tiny little training data set to get another neural network and train this entire process such that when we give it a new example, it can generalize effectively to this example and predict the correct label. Different algorithms correspond to optimizing different parts of this optimization process and optimizing them in different ways. The model-agnostic meta-learning algorithm optimizes for the set of initial parameters of this learning process such that one or a few steps of gradient descent produce a model that generalizes effectively from that tiny training data set. So that's how meta-learning works. What are these algorithms capable of? One thing that we showed recently that you can do with these algorithms is allow them to enable robots to adapt to new objects that they haven't seen before. For example, you can show the robot something that you want to do, like placing a peach into a bowl. It can adapt its weights to this task and to this object such that it gets a policy that can drop the peach into the bowl for different positions of the bowl. Beyond this one-shot imitation learning problem, meta-learning has also been successful at adapting to new molecules that it's never seen before, with potential applications to low-resource drug discovery. It can also be used to allow robots to adapt to new terrains and conditions that they experience over time. And finally, it's also recently been used to enable models to be adapted to new regions of the world for predicting the land cover segmentation of an image. So here are a wide range of applications of meta-learning that allow you to very quickly adapt a model to something that has changed about the world. Now what I'd like to talk about next is how we might go a bit further. So next I'll talk about capturing equivariances. And the motivation for this part is that there's actually a second solution to handling distribution shift, which is to try to build in structure into the model that captures the kinds of shifts that you'll see at test time. So for example, you can build in translational equivariance into a neural network using convolutions, and this will allow the model to generalize more effectively to data that has been translated. This is great when we know the structure and how to build it in, but unfortunately, oftentimes we don't know that, and this isn't a viable solution in those cases. So with this motivation, we wanted to see whether we could discover equivariant and invariant structure among a set of tasks using meta-learning, then build in that structure such that we can generalize effectively when given new data sets. So how do we go about doing this? One thing that we can do to think about this problem is thinking about how equivariances are represented in neural networks. And first, let's look at an example, specifically the example of convolutions. So here's an example of what a convolution layer looks like, where you slide a filter across an input X to produce an output Y. It turns out that you can represent this same convolution using a fully connected layer, where the weights of the filter are repeated across the matrix. They're essentially shared in different parts of the matrix, and the rest of the matrix is 0. Now with this example, what we're going to try to do is reparameterize this weight matrix to separate how equivariances are learned from the underlying filter parameters. So keeping along the example of convolutions, what we can do is we can reparameterize this weight matrix W into first the underlying filter parameters A, B, and C, and how these filter parameters are shared and copied within the weight matrix. And if you take the matrix vector multiplication of these two things, we get a flattened version of the weight matrix on the left. We'll refer to this matrix and vector as U and V, and essentially U can capture the symmetries, how parameters are shared, and V can capture the underlying shared parameters. It turns out that we can prove that theoretically this U and V can directly represent a decoupled equivariant sharing pattern and filtered parameters. And it can directly represent this not just for 1D convolutions, for example, but for all group convolutions with finite group G. This covers things other than convolutions like permutation equivariance and some forms of rotation equivariance. Okay, so now that we have a mechanism to separate out the equivariance from the underlying parameters, now we have a way to actually meta-learn equivariances that allow us to translate those equivariances to new tasks. In particular, what we'll do is in the inner loop, we'll only update the underlying parameters, keeping the equivariance fixed. And in the outer loop, we'll learn the equivariance U and the initial parameters. So essentially what we're doing here is training the model such that when you have these equivariances fixed and you update the underlying parameters, you'll get a model that generalizes well. And this will allow you, in situations where you have symmetries shared by a range of tasks, to potentially uncover these symmetries and keep these symmetries fixed when you're learning new tasks. We refer to this method as meta-learning symmetries by reparameterization, in the sense that we're reparameterizing the weight matrices in the network and keeping part of that matrix fixed and part of that matrix learned in the inner loop. Now, experimentally, we wanted to understand whether we could recover convolutions from translationally equivariant data. To study this question, we generated a number of synthetic tasks where each task corresponded to a different translationally equivariant function, and we had small data sets for each of the tasks. And from this synthetic data experiment, we found that MSR built on top of fully connected networks is able to perform just as well as MAML when you're using convolutional layers. And it's also able to significantly outperform MAML with fully connected layers and locally connected layers, indicating it's able to recover something that is as capable as the convolutional inductive bias. Okay, and further, we can actually show that with MSR, we recover a weight matrix that looks like this, that exactly corresponds to a fully connected representation of a convolution, where we have exactly the A, B, and C parameters copied across the diagonal of the matrix. Further, we wanted to ask whether we can recover something better than convolutions. To do this, we looked at first data with partial translation symmetry. So we took some locally connected functions with varying numbers of underlying filters, either one filter, which directly corresponds to convolutions, or 2 and 5 filters, which had only partial translation symmetry. And we find that in these cases, MSR is able to perform significantly better than MAML with convolutions because it's able to recover the correct symmetry underlying the data. Further, if you have data with translation, rotation, and reflection symmetry, MSR is also able to recover the underlying symmetries, in this case, rotation and reflection, when you build in translational symmetry, and perform significantly better than convolutions, which isn't able to capture the rotation and reflection symmetries. Great. Now, beyond these synthetic experiments, we wanted to understand whether we could learn from augmented real data. To do this, we constructed a meta-training process that looks like this, where we wanted to try to bake data augmentation into the architecture or update rule of the network. So in this case, we took the training set and the validation set for each task, and we augmented the validation set with different transformations of the data, and essentially trained a model such that when it adapts with an unaugmented training data set, it can generalize much further to augmented data. In this setting, we found that MSR is able to significantly outperform MAML and other variants across the board, and also perform comparably to prototypical networks when tested on OmniGlot, and significantly better when tested on the more difficult mini-ImageNet problem setting. Okay, so So kind of the takeaway from that part is that we're able to, by actually kind of recovering and encoding symmetries inside the neural network, we're able to generalize further, potentially, using this particular form of meta learning. However, we still need label data in this case in order to adapt. So what I'd like to talk about next is if we can fine-tune an adaptive distribution shift without any labeled target data. We'll specifically consider, in this case, a form of distribution shift called group shift. And what I mean by that is we'll have a categorical group variable z. This may correspond to the user, the location, the time of day, and can be easily derived from metadata. And we'll assume that our training data comes from this distribution and our test data comes from this distribution, where the distribution shift is captured by this underlying variable z. This can capture things like label shift and most forms of covariate shift, and it can also capture realistic problem settings like federated learning. Now, how do we go about solving this problem? So, previous approaches for tackling this form of distribution shift have built upon the idea of distributionally robust optimization. And the way that these algorithms work is they form an adversarial distribution Q of z, and they optimize for the worst case distribution over this variable. So for example, the worst case group. These approaches can enable robust solutions that are robust to the distribution shift, and they're less pessimistic than adversarial robustness techniques because they're optimizing over a smaller set of perturbations to the data distribution. But they often sacrifice average or empirical group performance as a result of optimizing for the worst case distribution. So we want to be able to overcome this limitation by adapting for distribution shift rather than trying to be robust to distribution shift. In particular, we'll assume that we have unlabeled data from the test subdistribution. So for example, we'll have new unlabeled data from a new user, a different time of day, or a new place. In the case of federated handwriting recognition, we might have unlabeled data that looks like this. And then we want to be able to use this data to adapt our model and infer the labels of these data points. And the assumption here is that the test inputs from one group, from one user, one time of day, and so forth, are available in batch or in a streaming setting at test time. We think that this is a fairly realistic assumption since oftentimes data is arriving from a single time of day or a single place at test time. We refer to this kind of general problem setting as adaptive risk minimization in the sense that at test time, we're given the opportunity to adapt our model. What the training procedure looks like specifically is we construct different subdistributions of the training data using our groups, and then we train for adaptation to each of these subdistributions. And in particular, this adaptation process, like I mentioned, will use unlabeled data. And we can experiment with a couple different meta-learning approaches to allow this fast adaptation to unlabeled data. This includes the model-agnostic meta-learning approach using a learned loss function, where we're running gradient descent on the unlabeled data using this learned loss. The second approach that we'll consider is meta-learning with a context variable, where we have a neural network that takes as input the unlabeled examples, produces a context, and uses that context when making predictions for the test example. In the simplest setting, this context variable can simply correspond to the batch norm statistics, where critically what we'll be doing is training the model such that when it's given data, unlabeled data in a group, it can use the batch norm statistics to adapt to that part of the distribution. Now, how does this work in practice? So on the federated extended MNIST dataset, we compared to a number of different approaches. We compared to empirical risk minimization, or standard neural network training. We compared to distributional robustness, like I mentioned before, and also a baseline that upweights the groups to the uniform distribution, rather than being skewed. And when we try to adapt to a new user using unlabeled data, we find that we're able to perform significantly better than these methods. So we compared to these methods, we also compared to a federated learning method, and the results are here. We see a 5% improvement in average accuracy, averaged across the users, and we see a 10% improvement in the worst case scenario, in a scenario where, on the worst user, essentially. And this evaluation is important because oftentimes you don't want your service or your network to work great for some people and work terribly for other people. We also evaluated on the CFAR-C and Tiny ImageNet-C datasets, and we were, in this case, adapting to new image corruptions. And we trained using 56 corruptions and tested using 22 disjoint or held out corruptions. And again, we find in this case that we see large improvements both in average accuracy and worst case accuracy, with an 8% improvement in worst case Tiny ImageNet-C performance and a 21% improvement in worst case CFAR-10C accuracy in the worst case. Okay, so to wrap up, if you take away nothing else from my talk, it's that there's this gap between our current paradigm and our current reality. In machine learning research, we often assume that we're going to be evaluating a static model, while in reality, the world is constantly changing. I talked about 3 approaches for trying to bridge this gap, starting with the general framework of meta learning for enabling very quick adaptation to changes in the world. I then talked about preliminary evidence of meta learning being able to capture equivariances in the data via reparameterized weight matrices. And I finally talked about how we can fine-tune and adapt to distribution shift with only unlabeled data. With that, I'd like to thank my students, especially my students and collaborators who did a lot of the work that I presented today, including Alan, Tom, Marvin, Henrik, Nikita, and Sergey. If you're interested in learning more, all of the lecture videos for my course on meta learning are available online, and I look forward to your questions. Thank you.